Welcome, everyone, to the April IMAG meeting, the Interagency Modeling and Analysis Group. And my name is Grace Peng from the National Institute of Biomedical Imaging and Bioengineering. And I am very happy to introduce Dr. Stephen Lee from the Department of Energy, who will be introducing our speaker for today. Stephen?
Okay, thank you very much, Grace. As Grace mentioned, I'm with the Department of Energy, and I am the Applied Math Program Manager. And I recently crossed paths with Grace maybe a week or two ago, and during her presentation, she mentioned that you folks were looking at doing a multi-scale modeling in AI announcement. So I quickly grabbed her after the session and mentioned that back in January of 2018, the Applied Math Program in the Office of Advanced Scientific Computing Research, which we call OSCAR, we had a big workshop in North Bethesda where we wanted to look at the use of machine learning for science across the Department of Energy. So prior to that meeting, I had tapped Nathan Baker and organized a committee to put together this workshop. And what we did is we had the workshop, we put together a report and a brochure, and we came up with some priority research directions for the use of machine learning for science at the DOE. So I thought it would be a good chance to have Nathan give an overview of what that workshop was about and the outcomes that we had. So Nathan is at P&L, but I can let him fill in the rest. Nathan?
Okay, great. Well, thanks for the opportunity to present. So my name is Nathan Baker. I'm the Director of Advanced Computing, Mathematics, and Data Division here at Pacific Northwest National Lab. I've been here for almost 9 years. Prior to that, I was a professor at Washington University School of Medicine. And I'm happy to say that I've been an NIH PI now for 15 years, still going. So although my research is pretty heavily applied math focused, we develop software supported through NIGMS for people understanding the properties of biomolecules and things like that. I'm also going to apologize up front if there's any background noise. It's spring break right now, and my wife and oldest are out of town doing college hunting. And so I'm at home with the boys and the dog, which could be the source of any noise you hear. Okay, so with that, I'll jump into this overview of our workshop and its results. So probably the most important thing you'll see in this presentation are those two links up at the start with the report and the brochure. The report is a very beefy document with lots of references. The brochure is a much more digestible executive summary, and I'd encourage you to check them both out. So as Steve mentioned, we held a workshop to try to understand the underlying research challenges and some of the priorities for those research directions. That was held back in January and February of 2018. There's information about that workshop at the link here. And the workshop was sort of sponsored and run on behalf of Steve, who introduced himself previously. So what we wanted to do, Barb Helland, who's the director of OSCAR, charged us with 4 things. And although some of these are OSCAR specific, just based on my experience with multiscale modeling and NIH over the years, I think many of them translate over pretty nicely. So we wanted to first understand the status, trends, and use of machine learning for scientific computing. Given that understanding, we then wanted to look at the gaps, or the opportunities, if you will, for where fundamental advances in the research of scientific machine learning could have an impact on scientific missions. The report focuses on scientific missions for Department of Energy, but it's actually, there actually are some biological examples in there, and it's not a very big leap to go from the multiscale modeling you see in DOE to the multiscale modeling you see in NIH, in particular NIBIB. So, and then we wanted to understand what the research directions should be to fill those gaps. So given the promise of machine learning and some of the challenges it's facing right now, what does the community need to do? What research do they need to perform in order to enable machine learning as a co-equal partner of scientific computing and scientific data management. And that's an important point. When we first introduced the term scientific machine learning, we got some pushback, or I guess comments like, oh, are you saying machine learning right now is unscientific? No, that's not what we're saying. But OSCAR for a long time has been focused on scientific computing, scientific data management. This adds sort of a natural third pillar to that group. Down here, there's my co-conspirators with the Scientific Machine Learning Workshop. Their names are all and affiliations are all listed in the report, and so this wouldn't have been possible without the support of Steve and this large group of folks covering pretty much the waterfront of scientific computing and machine learning. So, as I mentioned, what we want to do is make sure that that machine learning can be treated on an equal basis with the way we currently do data science and the way we currently do scientific computing or computational science. There's already plenty of examples where machine learning is being used in scientific applications. There's great examples of the impact that it can have, but there's concern, and I think well-founded concern, in how scientific machine learning and AI can be trusted. We have our scientific computing, so think about numerical partial differential equations or things like that. We have this data computing to the point where if you design a plane using those methods, you trust that the plane will fly. You design a bridge using those methods, and actually a great example is probably Tinsley Oden's work on using numerical methods to steer radiation therapy for cancer. And, it was a nice feedback loop where scientific machine learning was help parsing imaging, help directing the radiation therapy. We trust our computational methods to do those sorts of high regret tasks where you have to get it right. I think most of us, and you especially watch what happens with AI or autonomous functioning in vehicles right now or other places, probably don't trust machine learning to that same degree. We don't have the confidence to let it perform, surgery or design a plane right now, partly because we don't understand with the same level of rigor how it works, and we don't understand with the same level of rigor when it can fail. So that's what the workshop set out to do, to help define those challenges in the research that gives us that confidence and makes machine learning a co-equal in this scientific computing domain. So I'll say a little bit about the process because I think it's interesting. I wasn't familiar. I'd run a few different workshops for NIH, but I wasn't familiar with this process until I came to the national labs and started interacting more with the Office of Science. So there's a process that was developed by BES, Basic Energy Sciences, a couple of decades ago, actually, for how they explore an area. And this process is very rigorous. It's described online, and I can send you the link if anyone's interested. And it's designed to bring a set of folks together so that at the conclusion of 2.5 very long days, the community has converged on a set of research questions and a set of cross-cutting themes that represent their best understanding and their priorities for research directions in the field. This involves a couple different steps: a pre-workshop report that tries to lay out the state of the field, and then through the workshop itself, which definitely puts the work in workshop. It's a high intensity, 12, 14-hour days over 2.5 days to build and then refine these research directions. So that was essentially what happened during our workshop. We had a pre-workshop report. We had several plenary talks from Bin Yu, Roger Ghanem, Jake Shapiro, and Rafi Koifman to try to understand some of the outstanding challenges and inspiration in machine learning. And then we broke into groups and we worked on the priority research directions. We came up with these 6 research directions, which fall into sort of 2 different categories: foundational themes and themes for developing new capabilities. And I'll go through each of these in a little bit more detail in the subsequent slides. But they fall into the basic classes of domain-aware machine learning. You can think about that as not throwing out the baby with the bathwater. It's great to have things be data-driven. On the other hand, we have centuries of knowledge about how physical and biological systems work. How do we blend those two things together in a robust way? The advantage of doing something domain aware is that it also gives you a leg up on trying to interpret what the machine learning algorithm is telling you. Deep learning algorithms in particular are notoriously difficult to sort of analyze and figure out why they reached the conclusions they did. So this is a priority that can be facilitated by having that domain knowledge in the method. Robust, we would like to understand what it means for a machine learning algorithm to be well posed, to be stable, to behave as we expect it to behave. Data intensive acknowledges the fact that more and more the data is coming in very high dimensional forms, and our algorithms need to be capable of handling that. Modeling and simulation, and I can't resist telling this joke, Steve, I'm sorry. These last two were originally named inner loop and outer loop. So for those of us who, just think about these in terms of, how we think about control and other numerical methods, these sounded like great ways to describe our two algorithms, our sets of capabilities here. However, for those who live in the DC area and have to deal with the Beltway, inner loop and outer loop had very different meanings. So we renamed them. But essentially this first one talks about how do we use machine learning in the core on the inside of our algorithms. And then the flip side of that is what does it mean to have a set of either scientific processes or instrumentation, simulations that are steered on the outside by machine learning. So I'm going to jump into these and go into each one in a little bit more detail. I'll just echo what Grace said up front. I'm happy to answer questions as well as we go, or take them at the end. So please don't be shy and hesitate to interrupt. So this first one I said briefly as how do we throw the baby, or how do we avoid throwing the baby out with the bathwater? No models are perfect, right? There's the classic George Box quote that no models are perfect, but many of them are useful. And we've got centuries of information that have, built either physical models of how the world works or empirical models, as you often find in more biomedical applications, about how complex systems work. It would be a shame to throw that out and move entirely to a data-driven paradigm. And it'd be a shame for a couple different reasons. When we are reliant only on data, we can, as lots of reports have shown, introduce a tremendous amount of bias into the algorithm based on how the data is collected. We can also have the results of our algorithm be subject to the variability, the sampling error, the noise in the algorithm. And in general, these deep learning methods and related methods are very greedy. They will take as much data as we can give them, and it's often difficult to train when large labeled data sets are hard to find. Domain knowledge gives us at least the possibility of addressing each of those issues. First, addressing the issue of making sure that the model and the results of the model obey the physical rules or the empirical rules that we know about our system. Second, possibly regularizing the problem and making the system respond in much more controlled ways when new and different data, possibly with large amounts of noise, are introduced. And third, by ideally reducing the overall amount of data that we need for these systems. So many of you have heard of either reinforcement or one-shot or few-shot learning. That type of transfer learning is when one model is built using some data from one system and then applied to another system, thereby reducing the overall amount of data required for training. Domain knowledge offers a similar possibility. Additionally, domain knowledge contributes to the priority research direction I'm going to talk about in a second, which it also gives us a handle on interpretability. So by knowing that our model is obeying the laws and physical or biological models of the world that we believe, we have the opportunity to not just defend, but hopefully interpret some of what we see. I just want to briefly talk about this picture on the right here. So more and more we are seeing a class of algorithms called physics-informed machine learning or learning machines. And these are cases where, as you know, most machine learning algorithms have some sort of loss function associated with them. They're an optimization problem. Well, it turns out that most of our partial differential equations also result from a minimization of some form, essentially optimizing their own loss function. But in those cases, there's some description of the energy of the system, or it's a conservation law that's being solved. There's a natural framework for putting these two things together. What we don't have right now, and I think is really needed for biomedicine in areas like that, is a way to do the same thing with empirical knowledge. We have graphs of how we expect systems to behave. We have ontologies of complex system behavior. It's very hard to think about how to embed those in a rigorous way right now into our machine learning models. So this is my favorite priority research direction, so I spent more time on it. I'll jump to the others, through the others a little more quickly. But I think you'll start to see how these naturally build on top of one another. So as I mentioned before, one of the big challenges with algorithms like deep learning and other machine learning approaches is that interpretability can be very, very difficult. These convolution neural nets go through very many steps to basically wrap one layer into another layer, and unraveling those layers to understand why a certain inference was obtained is not straightforward. There's a lot of approaches. DARPA has an extended effort for so-called interpretable or explainable AI. This is different. This is asking, how can we take the scientific knowledge we have about the problem and use it to describe the features or the results of the machine learning algorithm? So we think that by either using scientific information on the front end to help build the models in domain-aware machine learning, or using them on the back end to help interpret the results, or parse the results, we can end up with a little bit more intuition and interpretability of the scientific machine learning results. And there's some examples over here talking about how the types of images one might get from either protein simulation or crystallography or cryo-EM can actually be broken down into features that help interpret why a 2D convolutional neural network classified different parts of the protein the way it did. This next one asks, what would it take for scientific machine learning to be robust? And in general, in scientific computing, when we say robust, we have something very specific in mind. We think about well-posedness and stability. That means as we perturb the inputs of our model slightly, we expect bounded perturbations on the output. We want to be able to understand the stability of how the results of our machine learning algorithm depend on the way we train it or feed it data. A complementary piece to that is these are, by definition, very nonlinear models. They're essentially a form of nonlinear regression. We would like to know under what circumstances a solution exists and whether or not that solution is unique. Now, the problem is the convolutional neural nets, deep learning, other types of machine learning algorithms are very, very high dimensional. So defining even uniqueness in those circumstances is very difficult. And so there's a lot of interesting research questions underneath that that kind of get at how we define uniqueness, how we define existence, what we mean by stability, so on and so forth. And this picture over here on the right shows how using rotational invariance and symmetry can actually help define identical flows in a fluid dynamics system. Okay, the next one also has a biological example. Again, this comes from a set of protein simulations, but you could also imagine a set of different images from electron microscopy or replicas from crystallography or what have you. And the question there is, how do we consume and interpret the large amounts of data that often has to be labeled by some other process? How do we train and identify and process those in a machine learning environment? And this speaks to most of the V to the N of the big V's of data, the velocity problems, the variety, and in particular the high dimensionality of the data, the veracity, the variability and things that go into it. There's a lot of underlying questions, mathematical questions about how to deal with high dimensional data sets with noise and make them useful for consumption by machine learning algorithms. And this actually, I think, underpins some new priorities from Steve's office about how to interface scientific machine learning with uncertainty quantification and other approaches for the statistics and mathematics of data science. So this next one is our inner loop example, and it essentially says, under what circumstances is it appropriate or even desirable to replace the traditional core components of scientific computing with a machine learning algorithm. So on the right here is a very specific example. Mesh refinement is usually a very deterministic, well-defined process for meshing domains that come from imaging or a computational model. However, when those domains move, they can quickly get themselves into trouble by tangling up nodes of the finite element mesh. So this shows how machine learning can be used to prevent that tangling and keep good quality meshes throughout the simulation. Other examples involve eigensolvers. When you need a few eigenvalues and maybe don't need them to super high precision, it's been shown that machine learning algorithms can get those much more quickly than our traditional linear algebra approaches, and so on and so forth. There's lots of examples for reduced order modeling, surrogate modeling, and things like that, where there's an ability to maybe add a machine learning component in what might look like a multi-fidelity framework. That's where the context of this call, that is different than the traditional numerical approaches, but gives you some advantage of scalability or speed or actually many other examples. There's lots. This is a huge, huge area. And the second piece is the flip side of that, which is when our processes, whether they're a scientific computing process or weighing instruments being used or steered, when those are surrounded by a machine learning driven control, what do we need to know about the machine learning algorithms? Which ones are most appropriate? How do we use them in high regret situations? For example, steering one of DOE's supercomputers or its high performance network or a very, very expensive light source. Those are examples where we need more information and more guarantees about the reliability and robustness of the algorithm before it gets used in high regret applications. So that is kind of a recap of our 6 priority research directions that came from the basic research needs workshop. As I mentioned, there's a lot more detail in the report, and my last slide will have those links again. You know, at the end of the day, the conclusion of the workshop was machine learning is here. It's already being used in scientific applications. It shows a lot of promise. So we need to understand how to maximize that promise and minimize the perils of things going wrong when you use it in scientific research. The research directions that we came up with, the 6 of them, build very naturally on the investments of Oscar and DOE's investments in general in applied math and scientific computing research over the past several decades. And we think it has a lot of potential for very, very positive impacts to DOE domains. But again, wearing my NIH PI hat, I also see a lot of opportunities in the NIH world too, particularly in the context of modeling biophysical processes, multi-scale modeling of complex systems and things like that. So this is my final slide. It lists those 2 links for the reports again. But we very much consider this a living document. Well, not a living document, but let's say a living process. I don't want to revise the report. Steve knows how much work went into that. But we don't want the conversation to stop. The workshop was a snapshot in time. This is a fast-moving field. These are very ambitious priority research directions. So we're looking for community engagement to understand how to move these forward, how to continue the discussions, how to identify other activities and partnerships that could drive these priority research directions together, and other things that we should be thinking about as a community regarding scientific machine learning. So that's it. There weren't any questions during the talk, so I hope there'll be some after.
Thank you, Nathan. That was wonderful. Our start off with the questions actually is in the more detailed report. I assume you'll provide more of like guidelines on how to use machine learning in certain ways, and limitations for certain applications, or maybe even, you know, benchmarking what different types of machine learning methods are used for in which application areas. Do you do that?
A little bit. You know, the report has 2 pieces. The primary purpose of the report was to outline where we see research gaps. And in fact, some of the questions you're asking are research gaps, right? Trying to find the right match between a problem and the algorithm and the way you train it and so on and so forth. There is an appendix to the report, which is fairly lengthy, that is this factual status document that gives an overview of the field as we saw it leading up to the workshop. It's a very fast-moving field, so it's not a comprehensive review, but maybe it is a way to get started with sort of understanding what's out there, how they're used, things like that.
Great. Thanks. Are there other questions, comments from Nathan? Please
Sure.
unmute yourself.
Sure. Nate, hi, Grace. This is Ken Wilkins from NIDDK. Nathan, great talk. I wanted to jump off your mention of that being sort of a living document and that appendix being a starting point. Is there any plan for some sort of one-stop place of how things evolve from where that appendix starts? Like, as you said, a cross-agency clearinghouse of information about how some of these things change over time in a rapidly moving field like this one? Or any plan for such a thing?
Well, I'm going to have to defer to Steve on that. I will say that I worked with the National Cancer Institute and did something similar for nanotechnology for several years. I led a working group kind of in the heyday. And that was very helpful for some coordination about research activities and things that were going on there. It's also a tremendous amount of work, which is why I'm deferring to Steve.
Right. And if you can hear me, I'll quickly add, there is an artificial intelligence interagency working group that is looking at coordinating activities among different federal agencies. But right now, the main task for that NIDRD group is there's an artificial intelligence R&D strategic plan that's being updated and will be issued sometime this month or next. But there is a need and a plan for doing interagency coordination out of NIDRD.
That's fantastic to hear that. But what is the name of exactly that IRG? That working group?
I don't know. What's the exact acronym? Do you know, Grace, for NIDRD, NITRD?
Oh, well, the NIDRD NIH is involved in, and I can appraise everybody about it. But it's interesting that there is a working group through NIDRD. I think the NIH also has another AI working group.
Yes, there is. Yeah.
The President's Initiative. Yeah. So, and there are other agencies on the call right now, as IMAG is interagency. I think NSF is on the call too. If you guys want to comment.
Hi, Grace. This is Vipin. Hi, Stephen.
Hi, Vipin.
Yeah. So, NSF does participate a lot in that NITRD AI program, and we also have our own internal AI group. Clearly, AI machine learning is being used very widely in almost all scientific areas. It's hard to find a proposal which does not use machine learning today. So it's very timely.
Right.
Agreed. I do like how this report, though, Nathan and Stephen, thank you, and everyone else who worked on it, has these areas in which that sort of are cross-cutting in terms of how it's being applied, domain specific, et cetera. So if there could be some way for agency coordination in the future to sort of follow these threads, that would help when you have certain research areas that may benefit from a given thread.
Yeah, that sounds like a good idea to coordinate, because a lot of people are using it in different ways, and it'd be good to have some sort of clearinghouse of success stories and what people are using and how they're approaching the use of machine learning. From my perspective, it's very helpful to actually bin them across these three capabilities, because some people, when they think of machine learning, the most common thought is to apply it to analyzing massive amounts of data. But then other people are interested in using machine learning to build better submodels within some larger multi-scale computation. And then the third group of people want to use it to maybe automate power grids, and more resilient power grids, or do better cybersecurity, or do better design of experiments. So just being able to bin things in 3 major use cases, I think, will be very helpful.
The last thing, the last interagency group I'm aware of that wasn't mentioned yet is, the Office of the Director of National Intelligence. So the intelligence community has something called AIM, AI, I forget what it's called. There's a report on the ODNI website that also talks about the intelligence community's interests. And, ever since I made the move from med school to National Lab and got more involved in national security, I've been surprised at the overlap between biomedical needs and intelligence community needs. So that would be another interesting point of connection, possibly, especially in the imaging domain.
Right, and I see Rachel Slayton, you're on the call. Rachel's from the CDC. I don't know if the CDC is also involved in some AI issues. Maybe you might need to unmute, but I had one more question, Nathan, in terms of how, and Stephen, how you conducted your workshop. You said that you actually had a pre-workshop report that you worked on prior to the workshop, and so then we're just trying to figure out our workshop at this point in terms of then how did you use the report during the workshop? Did you then use that sort of as a straw man to build on?
It was primarily intended to level the playing field. We were bringing people together from a lot of different disciplines. In fact, that was one of the, not a priority research direction, but it's definitely a priority social engineering direction, is trying to bring all of the necessary communities together. So the report first was intended to define sort of what the state of the art, the common language, common approaches, things like that. It was a straw man in the sense that while it didn't propose specific research directions ahead of time, we wanted that to be part of the discussions at the actual workshop. It became kind of a punching bag for all of the areas of machine learning that we had missed and the communities that we hadn't engaged. And so it was very useful to have something that people could react to ahead of time, both for setting common terminology, but also for kind of getting things off their chest. And it saved us wasting time at the workshop.
And I'll also add that pre-workshop, we really did emphasize that we looked at things through the lens of applied mathematics and scientific computing. And we want to understand the landscape of machine learning as of 2017, before we started 2018 in this workshop. So we put that stipulation up front, like, look, we're applied mathematicians. Here's the lens that we're looking through, and the report was broken down in terms of supervised learning, unsupervised learning, reinforcement learning. But the report itself, as you saw, breaks it out into a whole different set of categories, 3 of them foundational and 3 of them based on major use cases.
That's interesting. Very organized.
One of the themes that came up, I'm sorry, I had forgotten something before, and I keep remembering I'm on an NIH call. One of the themes that came up when they were talking about communities that we've been missing was the biostatistics community. So this came up many, many times, it's an area that seems like it's an appropriate thing to bring up with this group. So statistics in general, but biostatistics in particular, as an applied form of statistics, was suggested to us by many different people.
Interesting. We have some biostatisticians on the call.
Yeah.
Okay. Well, I don't want to keep you too much longer. Let's all thank Nathan and Stephen virtually.
Thank you.
Thank you for the opportunity.
Thank you. Great talk.
Thank you.
Thanks for sharing.